So we made it to the coding portion of exam 3. And so we have 3 differential equations, but we don't know the mole fraction of the air or the temperature coming out, but we do know the temperature of the feed air going in. And we're also going to say that the air going in is just going to be dry air. And then we also know the mole fraction of the humidity of the air, and we're going to say that the relative humidity of the air coming out is going to be 90%, and that will allow us to know the mole fraction. And then by giving an initial guess for the air temperature that's coming out, we can solve an IVP problem until we reach the other side. And as a result, we will find the temperature of the water coming out. We're going to find the temperature of the air coming in, and we're going to find the water vapor of the water vapor in the feed air. And if we don't get that initial guess correct on the first try, we can keep changing that guess until we reach a desired feed value. And so let's start by how we usually start, and we want to import numpy because we're going to be doing numerical calculations, and we're going to abbreviate it as NP per usual. And then we want to, we're going to be creating 3 different subplots. So for those 3 differential equations with the water vapor in the air, the temperature of the water coming out, and the temperature of the air coming in. So we want to make those subplots so we can see them side by side. So of course we'll be using Plotly. And then, like I said, using that IVP, we'll need to use SciPy and the integrate package. So from SciPy, and then we're solving an IVP problem. And then eventually we will also be using the optimize and import root function, but I will explain that later. Okay, that looks like it. Enter. So now I want to talk about these variables here. I just typed them out beforehand because it will be easier just to explain than to copy all this down from given information. So this H here is just that heat transfer coefficient, and it's just going to be 10 in this case. This is just the gas constant in terms of joules per mole per Kelvin. We have the density of air in kilograms per meters cubed. And then we have the heat capacities for air, the water as a gas, so that water vapor, and the water as a liquid. And you can just find those online. Like here we have some for air, and it's just about 1,000 if you put it into kilograms. And here's for water, and it's about 25 degrees Celsius for that feed air. So we can just round it to that 4,190 joules per kilogram per Kelvin. And then what we have here is the enthalpy of vaporization. And then this just comes from that Lewis relation that we described in part A of the exam, which is just that Lewis relation between the H over Kc and the rho Cp, and you just rearrange it. And then, so now we also have a packing material in our column, and we want to know how much specific area is going to be supplied to this column. And so this is just that specific area. And then we have the molecular weights of air and for water, and You can just look these up as well, but off the top of my head, I know water is 18 grams per mole, so just converting it to kilograms, multiply that 10 to the negative 3. And then the velocity for that air coming into the tube is just 5 meters per second, and the liquid flow rate for the water is kilograms per meter squared per second, and just the atmospheric pressure, so the pressure for that feed air is 101,325. And then the height, the length of the column of that cooling tower is just going to be 20. So what I want to do is I want to first correct myself. The incoming air is actually going to have a 50% relative humidity, so it's not going to actually be dry air. And so the situation here is that there's hot water coming down this cooling tower from the top, and then cooler air at 25 degrees Celsius is going to be blown upwards. And so let's put those in here. So we have that feed water, and it's going to be at 70 degrees Celsius, but since we're going to be using the ideal gas law throughout this problem, we want to just convert them to kelvins so we can eliminate some errors. So to do that, you just add 273.15. And now I'm going to do the same thing just for the temperature of the air coming in. Except it's going to be 25 degrees Celsius, 273.15. And so then we want to look at the mole fraction of the water vapor of the air, and we're going to just call that YA. And this is going to be for the feed. And there's going to be that 50% vapor pressure, like I said. Whoa. And then we're going to multiply that by the partial pressure of the water vapor. And if it was 100% humidity, then our partial pressure of our water vapor would actually equal that saturated vapor pressure at the temperature of the air. And then we also need to look at the gas flow rate, but there's two parts to the gas flow rate because we have two gases involved, which includes the water vapor and the air. Oh, and then this will be over the atmospheric pressure, which we defined earlier. Yes. And so that we're going to start with the gas flow rate of the air. And that's just going to be that atmospheric pressure, the molecular weight of air over that gas constant multiplied by the feed air, the temperature of the feed air, and then times that velocity of the incoming air feed. So now we also we're going to be plotting this, and these derivatives are going to be in relation to time. So when we plot, we want it to be over time, over distance. Over distance. And so I'm just going to use NP ln space. And then this first number is just going to be from 0 meters to 20 meters, but we already defined that as height. And then I can make a certain number of intervals, which to make them evenly spaced, and I'm just going to do 21. So now we want to define a function. So we want to find the saturation vapor pressure using the Antoine equation, and it will return the vapor pressure. So this is going to be log base 10, and now I want to find those coefficients. So this is the Antoine equation here, the formula, and then oops, that is not what I wanted. I need to find those coefficients. So, are they... Okay, this looks about right. So A is 8.071 and B 1730 and C 233.426. Okay, so I'm just going to input that in here, and I'm going to make an equation for it. I'm going to define an equation. So I'm just going to have it as that the vapor pressure, that's what we want, and have it in terms of temperature. And then I wanted to return the Antoine equation, the solution from the Antoine equation. It's going to be 10 to the power, so we can get rid of that log base. And so we're going to start with that A, which was at the 8.07131, I believe. 131.1730. 63, and then the B is going to be that 1730.63 all over, and then C, which is at 233.426. 233.426 plus a temperature minus 273.15, because for the Antoine equation it's in degrees Celsius. And then the pressure is going to be returned in milligrams of mercury, but we're going to want it in pascals, so we're just going to divide it by the conversion, which is just 760 times 101.325. That looks pretty good. So now that we have these given parameters defined, we want to solve the differential equations, the three that we found in part B1, and we want to return the right-hand side of those differential equations. So let's define the equations first. A function. So we're going to have that function as that dy, so the mole fraction, the temperature of the water, and the temperature of the gas. And then we have the independent variable as the direction, the distance of the column, the length of the column, and then the dependent as a vector. So we just put that as v. Alright, so now what I want to do is I want to just redefine these variables. So what we're going to be getting out is that mole fraction. And that's going to be in the vector as the first element in there. And the indexing starts from 0 for Python, so it's going to be 0. Now this is just going to help us eliminate or reduce any errors, just so we can visually see it better. And the temperature of that water is going to equal the second variable out of that array. And then the temperature of the gas is going to be the third one of that array or vector. And so now what I want to do is I need to enter in those differential equations that we found and derived in part B1. So let's start with that change in the mole fraction. So we have that negative specific area multiplied by that molecular weight over the total gas flow rate multiplied by the molar flux of the water at the interface. So that also means that we need that molecular, that molar flux. So that molar flux can be defined as that mass transfer coefficient over the gas constant over that temperature of the gas multiplied by the partial pressure of the vapor at the temperature of the water, and then minus the mole fraction of that water vapor multiplied by the total pressure. So now let's move on to that temperature of the water, the difference in the temperature of the water through the column. And so that's going to be that specific area all over that liquid flow rate over that the heat capacity for that liquid water. And then multiplied by the heat transfer coefficient multiplied by that driving force, so that temperature of the gas minus the temperature of the water. And then subtracted by the heat of vaporization multiplied by the molar flux. Now for the last one is the temperature of the gas. We have that specific area once again multiplied by the heat transfer coefficient over the gas flow rate over that heat capacity for the gas, and multiplied by that temperature difference that starting from the gas minus the temperature of the water. And so now that we have the total gas flow rate, and so we have the total gas flow rate from part B1, and I derive how to get the gas flow rate of the air utilizing partial pressures, or mole fractions, molar concentrations. So what I do now is I want to add those in. Let's see, where do I want to put those? Let's just start it up here. Okay, so we want the gas flow rate, which is going to be that mole fraction over 1 minus y, which would give us the mole fraction for the air. And then you multiply that by the flow rate of the air, the gas flow rate of the air, multiplied by the molecular weight of the water all over the molecular weight of the air. And then I want the total gas flow rate, which is just that gas flow rate of the air plus the gas flow rate of the water. And then we want that average molecular weight. So we also found those in part B1. And so the average molecular weight would be the gas flow rate of the air plus the gas flow rate of the water, and put that all over the gas flow rate of the air over the molecular weight of the air, plus the gas flow rate of the water over the molecular weight of the water. don't need that parenthesis. Okay, so we also have this heat capacity for the gas. So we need to compute that. So we have the heat capacity of the gas, and we can get that by the molar concentration, no, the heat capacity of the air multiplied by the gas flow rate of the air, plus the heat capacity of that water in the gas phase multiplied by the gas flow rate of the water. And then you want to put all of that over the total gas flow rate. So this HV is actually the enthalpy of vaporization, just as a correction. And now what I want to do is I want to solve for the differential equations. Solve equal solve. Oh, and actually what's important is we need to have a global sol. And what this will do is it allows us to use the values within this function, what we solve, to be used outside. And so we want to solve that IVP. And so we define the function that we have, so that dy, tw, tg. And then we need the range for the independent variables. So that will be from 0 to that height, which is 20. But we can type in the variable that we have as height. And then we need initial guesses. So we need to add some code. And we need to, actually this goes here. Let's put it here. We want to put the initial guesses that we have. So we want to put the guess that we have for the exit of the exit mole fractions, which will be a feed multiplied by, let's say, a factor of 10%, so 1.1. And then our guess for the temperature of the gas exiting will be the temperature of that feed air. And let's say we add 5 kelvins. And we're going to have sol equal none. So that will just give us an empty variable that we can use for a solution later. Okay, so then we have those initial guesses and we want to put that in. So we have those initial guesses, and let's see where we put those in. Where were we? Oh, here. So we have those initial guesses, so we need to make sure that we have the order right. So we're starting from the top of the column and going down. So we already know the initial water temperature. So we'll put that in. So we have the exit temperature of that mole fraction and the temperature of that water feed, and then the temperature of that gas feed that's exiting. I need exit. And then I need the method, so we're just going to use the Radu for the IVP. And then I'm going to have the dense output and set it equal to true. And then what this does is it allows us to evaluate the solution at any particular time. And we need to at any particular time. So then what we need to do now is we need to set up some locations to solve our solution. And we just need to set some locations that we can solve our solution. So we want to evaluate our solutions at zplot, which I think we did up here. Oh, maybe we didn't. Oh, here we go. Yeah, I thought we did it. So we have that that zplot. So let's just add that in. So we have that, actually, that's where we're evaluating this whole IVP. So dot solve, and then we will just put the z underscore plot in those parentheses. So now what we want to do is we want to create a function because we want our initial guesses to converge. And this is where our root finding is going to come into play. So first I'm going to define that function as converge feed, air, temperature, and that mole fraction. And we already have a vector, so I'm just going to label this as v2. And then we have our exiting mole fraction as a guess, and this will be the first thing in the array. And then we have our temperature of the gas exiting. Oops. Okay. And so if our initial guesses for these this y exit and the temperature of the gas exiting are incorrect, the root finding is going to help us adjust our initial guesses until we get our desired value. And so we're just redefining these because it will make it easier and help reduce errors, just kind of like this. And when our initial guesses are correct, this function should return values of 0 from the root finding. Okay, so now we want to move down here, and we want to return values for this function. So first, I think I need to indent this. Yes. And I think it goes like this. Let's see, we'll try it. So now I want to return values. So I'm going to return values for the those initial guesses and for the solve IVP. So and now I want that first thing in the array, or the first row, and then I want the last element. And then I'm going to subtract that by the feed, the mole fraction in the feed error, in the feed. And then I want to look at the temperature of the gas. So I'm gonna look at that second thing, and then we want the last value again. And now I want to subtract this by the temperature of the air in the feed. Okay, that looks good. Okay, but now there's some errors up here. Okay, that's supposed to be guess. And this is supposed to be a plus. And then this is supposed to be capitalized. That should help. Okay, so let's re-execute all this. It seemed to work. That seemed to work. Let's execute this. Okay, cool. So now what I need to do is I need to execute this root finding. But first I forgot to, first I misspelled this, and that's Radul. And then I forgot to return the values for this. So I went for this function within it. So I want to return the dy, dtw, and dtg. So those derivatives that we want. And then, okay, so now I think we're, well, let me shift enter. Now I want to do that root finding function. So that function is going to be that converge, there it is. And then I want those initial guesses, which will be that y exit, and then we guess, and that tg exit underscore guess, and that should be good. Alright, so there we go. And now what we need to do is we need to plot these still. So it's going to be a figure, and we want to make those side-by-side subplots. And I want there to be 3 rows and just 1 column. So first I'm going to make that figure, or add the scatter plots. And the x-axis is actually going to be that z underscore plot, that distance of the column for all of these subplots. And then the y for this one is going to be that, so we want that first element, so we want that, where is it? So we want that mole fraction first, and then instead of having the last value, we want to have put in all of the values for the plotting, for plotting purposes. That's helpful. Okay, and now I want to name it, and this is going to be the mole fraction of that water vapor. And then I'm just going to give it row, put this in row 1, column 1. Let's see, does that look good? Okay, so now I want to copy and paste this because the rest of the scatters are just going to look similar. And instead of 0, it's going to be 1 for that temperature of the water. Switch the names, and this is going to be row 2. And now the same thing, but for the temperature of that gas. It's going to be row 3. Okay, so these are kind of long, so I might want to update the figure. And change the layout. So maybe I'll make the width equal 600, and then the height equal 900. Alright, that looks a lot better. And then here are our scheme. So we know the, what is it called? A legend. So here's a legend so we know each graph and what it's graphing.